Once again, I welcome you all to the lecture series of Mechanics of Solids. Today, we will discuss an interesting topic. It's a very interesting topic, which is the theory of failure. Theories of failure, not theory of failure. So it is something to do with failure. It's not talking about failure. Instead, these theories of failure will help us to design something in the safe zone. So as an engineer, as a mechanical engineer, as a design engineer, this should be there in your mind always. You cannot forget this. You cannot keep this aside before you move into any kind of design. So these are some guidelines given to us to do a safe design. I hope you might be remember about the factor of safety that we have discussed. Something that is related to the safety. So this theory of failure will also guide us to design things in the safe zone. And it has a close relation with all the topics that we have learned till now. That means theories of, if you want to understand the concept of theories of failure, you refer back to the previous lectures on principal stresses, principal strains, strain energy and all those things, because we are going to discuss theories of failure in those contexts. So a better understanding about those topics will definitely help you to understand theories of failure better. So you can consider this lecture as an introductory class for all the theories of failure. Okay, so let's define one by one. In this class, we are going to define about the maximum normal stress theory, right? So how these theories are being defined. Before moving into that, let's have a brief discussion about the theories of failure. How can we define a failure? That's the first question we need to answer before moving into the theories of failure. See, failure is not the breaking of material into two. No, that is not always called as a failure. Obviously, that is a type of failure. But when we talk failure in terms of mechanical engineering or mechanical parts, we have to redefine it. If a component has deformed or has undergone any kind of change which make it inappropriate in that particular application, then that is considered as a failure. Suppose you consider a shaft which transmits some amount of power, and after some time, after the application of some load or after some course of time, some kind of bending, permanent deformation has happened to the system, and after that, when we switch on the system, a severe vibration is going to develop in the system. That means the shaft didn't break apart, but instead it has permanently deformed, and the sole purpose of the shaft is not satisfying. That means it's not transmitting any power, instead it is creating large noise and vibration. In that, such kind of cases are also considered as what? Failure. So anything which is beyond application, anything which results in a component not suited for any application is considered as failed. That is the scenario we have to talk. Now, if we consider failure as permanent deformation, or how can we theoretically write deformation? Theoretically, say a material is failed or deformed permanently, which makes it inappropriate for an application. It's very simple. We know that by the stress strain curve, let's say this is how the stress strain curve is going to look like. We know that beyond the point yield, the material is in the plastic zone. This is in the plastic zone. Plastic zone means some kind of permanent deformation has happened in the material, which is considered as a failed component. Okay, so generally, something which is there in the plastic zone generally is considered as failed. But for some cases, we say that beyond ultimate is considered as failed. So only thing wherein which we can say whether a component is failed or not is simply by comparing it with the yield value or the ultimate value. In very simple words, I can say that when I apply a certain amount of load in a material and the developed stress within the body crosses the yield stress or the ultimate stress, it is considered as a failed component, right? So in In short, I can say that the allowable value should be very much lesser than the ultimate value or the yield value. This is a simple words. We know that the material is working in a critical condition if the stresses are close to the yield value or the ultimate value. So we have to design a component where the internal stresses developed is far behind the ultimate or the yield value. That is the ultimate aim. So everything is limited or discussed in terms of the maximum allowable value. We know that a material will fail when it crosses the ultimate value or the yield value, or it crosses the maximum shear stress, maximum yield shear, or ultimate shear. Or we can say that a material will fail if the total energy or the strain prime or the maximum strain has crossed beyond a particular value. The principal strain or the maximum strain developed in a material goes beyond a particular yield value or yield strain, it is considered as failed. Or in other words, we can say that if the energy has crossed a certain threshold, it is considered as failed. So these are the different theories of failure, where we have generally we say that we have 5 theories of failure, and the first one is the maximum principal stress theory, which is based on the normal stress, and the second one we have is the maximum shear stress theory, which is based on the maximum shear toe, and the third one is based upon the maximum principal strain theory. It is based upon the strain, the displacement. The fourth one is based upon the strain energy U, and fifth one is also based upon the strain energy. So one by one we are going to discuss all these 5 theories of failure. Now let's move on and discuss the maximum principal stress theory. So as the name suggests, maximum normal stress theory is something related to the maximum normal stress sigma n. So we have learned about this maximum normal stress in our initial classes, where we told that when we apply a set of loads on a system, there will be 2 types of stresses that will generate within the material. One is the normal stress and second one is the shear stress. And we have learned the equations to calculate the normal stress in any plane, right? And we have learned that the maximum normal stress is the principal stress. I hope you all remember this concept. The maximum value, possible value of the normal stress that develop within a material is the principal stress. That means if you have a set of loading, say sigma 1, sigma 2, sigma 3, led by sigma x, sigma y and sigma z, and if you calculate the maximum normal stress, say sigma 1, and maximum normal stress theory states that if this value of sigma 1 is greater than the value of sigma y, it is fail. It's a failure. And this is the simple way of explaining the maximum normal stress theory. But as I told you that we are talking all these theories of failure in the light of safety. If in that case, if we have to define the maximum normal stress theory, then we should define it like the developed maximum normal stress should be less than the yield value, because I told you that whatever which is or what this, if the stress goes beyond the yield value, it goes to failure. That's how I defined it, right? So the value of stresses should be way less than the yield value, right? So, or more precisely, we can say that the maximum principal stress should be less than the allowable stress. This is the most safe design. This is a critical design where the maximum principal stress crosses the yield value or the ultimate value, system fails. That is the ultimate meaning of it. But for the safe design, the maximum principal value should be less than the allowable value. When we talk about the allowable stress, definitely we have to bring factor of safety into account. That means sigma allowable is nothing but sigma yield by factor of safety. This is how it is being defined. So the generated normal stress, maximum normal stress, none other than the principal stress, should be less than the allowable value. Now how this safe zone will look like, right? So if we talk about the three-dimensional case where you have the maximum principal stress of sigma 1, second maximum of sigma 2 and third maximum of sigma 3, it has to be plus or minus yield, plus or minus yield, or plus or minus yield. Or if we consider that we have a plus sigma y and a minus sigma y, then we have three different equations. One is sigma 1 plus sigma y by 2, sigma 2 plus sigma y by 2, sigma 3 plus sigma y by 2, and another 3 set. So these are the 3 plus 3, total 6 set of equations. And if we plot all these equations in 3 dimension, it is going to be something like this. It is going to be something like this. If I rub all these things, we have 3 principal axes, sigma 1, sigma 2, sigma 3. If we write sigma 1 is equal to sigma y, one phase will come. Sigma 1 is equal to minus sigma y, next phase is going to come. Similarly, if we plot all these equations in the 3-dimensional plot, it is something like a cuboid. I think it is better if we limit our discussion to 2 dimension, where we have sigma 3 equal to 0. If that is the case, we have the equations like sigma 1 is equal to plus or minus sigma y, sigma 2 is equal to plus or minus sigma y. Now let's plot this set into our 2-dimensional axis, where this is going to be sigma 1, this is going to be sigma 2, but we can say that if sigma 1 is equal to sigma y, that means this is how the line is going to be. Sigma 1 is equal to sigma y. Now if sigma 1 is to be minus sigma y, then this is going to be the line. This is going to be sigma 1 equal to minus sigma y. I will do one thing, I will bring all these things a bit more closer to have a better idea. So this is going to be sigma 1 equal to positive sigma y, and this is going to be sigma 1 equal to negative sigma y. Similarly, if you consider the other two, sigma 2 equation, sigma 2 is equal to positive sigma y is this line, and sigma 2 is equal to negative sigma y is going to be this line. That means we can say that this is the safe zone when we design. That means if you take a stress here or stress here, or any stress that comes within this 4 boundary is in a safe zone. Or in other words, I can say that, or we can say that, if we design some component based upon this stresses within this limit, it is a safe design. It can be considered as a safe design. So this is how the plot of maximum normal stress theory will look like, and this is the area in which this normal stress theory is going to be valid. Now where all we can apply this theory? So basically this theory is suitable for safe designs of machine components made of brittle materials under all type of loading. That is another important thing. This is not suitable for the safe design of ductile materials. You might be wondering why we use brittle materials, or what is the speciality of brittle materials, and why we can't use ductile materials, the failure criteria using for the ductile materials. The reason is very simple. If you refer back to the stress strain curve lecture, I have clearly stated that ductile materials fail by shear. It is not fail by normal stress, it's failing by the shear stress, whereas the brittle materials fail by normal stress. So because of that reason, we use normal stress theory for the design of brittle material and shear stress theory for the design of ductile material, which I will discuss in the coming lectures. Okay. And ductile materials are weaker in shear, that we have already discussed, and this theory can be suitable for the safe design of machine components made of ductile materials under the following condition. There are limitations. There are special cases where the uniaxial stress, maximum stress, tau max is sigma 1 by 2. This I will, uniaxial case we have only one value. In the uniaxial case we have only one stress value, sigma 1, and tau max is going to be, we know that tau max is equal to sigma 1 minus sigma 2 by 2, right? So if that is the case, then for uniaxial case sigma max is going to be sigma 1 by 2, that is being denoted here. In that case we can, if we use sigma 1 by 2 as the limiting value, then we can design the ductile materials under the uniaxial condition. Now we have another condition, biaxial state of stress when principal stresses are alike in nature. Same definition I can give, because even though we can define this or design these ductile materials using the sigma values, ultimately it is correlating to what? Maximum shear values. That's the only meaning. Even though you are using the maximum normal stress theory, but ultimately when you go back or when you go behind the derivation, you can see that it is ultimately relating to the shear stress only. Even though in the front page you might be seeing you are equating with the normal stress, but behind the screen it will be actually equating with the shear stress. And also hydrostatic state means you have three mutually perpendicular stresses acting in three mutually perpendicular directions. If that is the case, maximum shear value is going to be equal to maximum normal value. So these are the three different cases where we can use the maximum normal stress theory if we are designing the ductile materials. But to conclude, I will say that the first two statements are very important, and that's how we use it, because when you learn the maximum shear stress theory, you will understand. So it is always recommended that for brittle materials you use the normal stress theory, and for ductile materials shear stress theory is better. I didn't say that it's the best theory, because we have different other theories also. So once we complete all the 5 theories of failure, you will understand which one is considered as better. So this betterment is purely based upon the area under which the design is being considered as safe, the zone, right? So that's all for the biaxial state, sorry, not the biaxial, normal stress theory. And in the next class I will discuss about the maximum shear stress theory. So this maximum principal stress theory is also called as Rankine theory. So this is another way of calling it. Sometimes in the examination they can ask you what is explain the Rankine's theory of failure. Next we will discuss the Guest or Tresca theory of failure, because these theories are being postulated by different scientists, and these theories are given different names. So right now we have completed the Rankine theory, and next class we will discuss about the maximum shear stress theory. Thank you.